Okay, so I think I'll start now. So today we'll be learning about rotations and circular motion. So first, let's talk about uniform circular motion. So uniform circular motion is the motion an object has along a circular path where there is no change in speed but a change in direction. So as you can see in the diagram, the speed is always constant, like this one. Except the speed is always changing based on where it is on the circle. And nothing about it, the speed is that it's always tangent to the circle like this. So it's always tangent right here, no matter where it is on the circle. This also means that the distance an object travels in uniform circular motion will be the same in each section of time. So let's say that an object travels this one, like a distance from here to here. It's going to be the same from like all points. So like each second, the distance an object travels along the circular path will be the same. Like if we're saying that this is 1 second, then these are all going to be the same distance. So an important equation when talking about uniform circular motion is centripetal acceleration. So right here, if you draw a circle like this, if the velocity is tangent, then the centripetal acceleration is always pointing inwards, and it's always perpendicular to the velocity. So if there's velocity like this, then the acceleration is always going to be like, and again, it's always pointing inwards. And the equation you use is the centripetal acceleration is equal to the velocity squared divided by the radius. And the radius is just the distance from the outer circle to the center. So these are all ours. So now we'll talk about uniform circular motion for dynamics. So in this diagram right here, you can see that there's a velocity and the centripetal acceleration is pointing inwards and they're perpendicular, and there's also the radius. So the centripetal force is, well, first of all, the Newton's second law is the net force is equal to the mass times the acceleration. And to find the centripetal force in a uniform circular motion, you just plug in the centripetal acceleration. So it would be m times v squared over r. So the centripetal force would be mv squared over r. And we'll learn about uh, angular velocity different times, so you don't have to worry about this part. So for uniform circular motion dynamics, if a particle of mass m moves at constant speed v around a circle of radius r, like this one, then it always has a net force of magnitude mv squared over r pointing towards the center of the circle. So the centripetal force is the same as it goes in the same direction as the centripetal acceleration. So it's like this. At all points along the circle, it's always pointing towards the center of it. The force is always trying to move the particle to the center of the circle, and without this net force, the particle would move off in a straight line tangent to the circle. So, if there is no centripetal force, for example, in this one, if there's no centripetal force, then if the object was spun, then it would just go tangent to the circle like that. And now we'll talk about period and frequency. So the period of So when an object goes around a circle once, or when it completes one revolution, it is called a period of the motion. So it's represented by t, and the frequency shows how many revolutions there can be in 1 second, and frequency is shown by using the symbol f. So like that. This is period and this is frequency. And the equation to find frequency is 1 over t. And likewise, the equation to find t is 1 over f. And these are two important equations when talking about circular motion. And unit for frequency, since the period of motion t is the unit for that is in seconds. So 1 over, if you're using this equation to find the unit for frequency, it would be 1 over seconds, which is just the inverse of seconds. So s to power -1 or 1 over s. And now we'll talk about the velocity equation. The equation for velocity using period t is shown down below. So in this diagram, you see that so first of all, we know that the velocity is equal to the distance divided by the time. And for a circle, the entire distance of a circle is just the circumference, which is the pi times the diameter, or the diameter can be 2r, which is 2 times radius times pi. So we write this equation as v equals the circumference divided by the time, which is time for a circular motion is also the same as the period. So you can write t is the same as the period. So it'd be c over the period. So it'd be 2 pi r divided by the period. And that's also an important equation to know when talking about the circular motion. And then you can also use that in the centrifugal force equation. So where that if v is equal to 2 pi r divided by the period, then the centrifugal force would be m times here 2 pi r over t squared divided by r. So that would be m times 4 pi squared times r squared over t squared divided by r. And that would just be equal to m times 4 pi squared r divided by t. So that's if you don't know a, if you don't know, if you have like the period and the radius, so you can just use this equation instead of this one, instead of mv squared over r to find the force. You can use m times 4 pi squared times r divided by t, which is the period. Okay, so you can have 3 minutes to do this first example question. And if you have the answer, you can just message it to me in chat. Okay, so for this first question, it asks, a ball is attached to a string that is 1.5 meters long. It is spun so that it completes 2 full rotations every second. What is the centrifugal acceleration felt by the ball? So if you draw a diagram, it would be like this string, which is 1.5 meters, and the ball like that, and it would be traveling along a circular path. So it says it has spun 2 full rotations every second, which means that the t is equal to 2. Oh wait, hold on. Um, oh sorry, like the frequency is equal to 2. So first, we're trying to find the centrifugal acceleration. So if we had the formula v squared over r, we know r, which is 1.5 meters. So we're trying to find v. So based on the equation we found before, v equals c times the the frequency, or 1 over t. We can write that as c times f, which is 2 pi r times f, or 3 pi times 2. So the answer would be 6 pi. So the centrifugal acceleration would be 6 pi squared divided by 1.5, which would be 237 meters per second squared. So you guys could do have 3 minutes to do example 2. Okay, so for this question, it says an audio CD has a diameter of 0.12 meters and spins that up to 540 RPM. When the CD is spinning at its maximum rate, how much time is required for one revolution? If a speck of dust rise on the outside edge of a circle, how fast is it moving? what is the acceleration? So if an audio CD has a diameter of 0.12 meters, then the radius is 0.06 meters. And I wrote here that the 540 RPM is also just 9.0 s to the negative 1. So it first asks how much time is required for one revolution. So it's 1. T is equal to 1 over 9. So the answer would be 0.11 seconds. And then it asks if a speck of dust rides on the outside edge of a disk, how fast is it moving? So it's asking for the velocity. So we know the velocity is 2 pi r times t. And so it's, we know the r is 0.06. So 0.606 times 2 is 0.12 times pi. And then we know that the t is 0.11 seconds. So if you solve that, you would get 3.4 meters per second. And then it asks, what is the acceleration? So for to find the acceleration, we would just use the centrifugal acceleration equation, so v squared over r. And we know v squared now is 3.4 meters per second, so it would be 3.4 squared divided by r, which is 0.06. And you would get 190 meters per second squared. So that's how you do that question. So now, again, we'll talk about the velocity vectors. Velocity vectors we talked about before, so I'll talk about them again. So even though the speed of an object moving in circular motion will be constant, the velocity vector will be changing. So even though the speed is always the same, it'll always be changing directions, and it'll always be also changing to the circle. So the direction of the velocity vector at every instant isn't a direction changing to the circle. So now we'll be talking about the maximum motion speed. So when you walk or run or just walk, then you're actually having a circular motion because your hips are moving. So your walking speed has a limit, and the limit is set by circular motion. When you move, you are taking strides and your body is in circular motion when you pivot on your forward foot. So the forces that are acting on you when you're walking are your weight and your normal force. So it's W weight minus the normal force. And your net force is also equal to, since it's in a circular motion, it's equal to mv squared divided by r. And because your weight is pointing down and your normal force is pointing up, you want your normal force to be as small as possible to have the most walking speed, because in a circular motion, the net force is always pointing to the center, and in this case, the center is going down. So having so if there's no normal force, then everything's just pointing down, and if the normal force is larger than the weight, then it would be pointing up. So that won't work. So in this case, we assume that the normal force would be 0 to have the maximum walking speed. So if the net force equal to n minus 0, since we're making normal force 0, and that means the net force is equal to the weight is equal to mv squared over r, and we know that the weight is equal to mg. So we cancel those out, and we get v squared over r equals g. So we find that the maximum walking speed is root g times r, and r in this case would be right here. The distance from the distance of your leg, the length of your leg. Now we can talk about the centrifugal force. So forces that seem to push an object to the outside of a circle is called a centrifugal force, because this isn't an actual force and only singular terms compared to centrifugal forces, which are on a moving object, or that an object moving in a circle has, and is always pointing inwards. Centrifugal forces don't appear on free body diagrams and are included when using Newton's laws. The centrifugal force makes them think they are being pushed outward. However, the only actual force is the contact force of the cylinder while pushing inwards. And this, what I said right here, is actually an example to a ride where it spins you around really fast and you're stuck to the wall, and they eventually remove the floor and you still won't fall. So now I'll talk about the apparent weight. So there are many examples of apparent weight in circular motion. For example, when you swing a bucket of water over your head quickly, it stays in the bucket and nothing spills out. When you swing it slowly, it'll spill. And another example is when you're on a roller coaster and the cart is able to stay on the track even when it's upside down. And when you feel more weight on you when you're moving, when you're on the bottom, you're moving upwards and when you're on the top, you feel weightless. So first I'll be talking about why, I'll be explaining why you feel heavier when you're at the bottom of a roller coaster. So when you're at the bottom of a roller coaster, there is a weight and normal force acting on you. So in this diagram, I'll draw it again. If you're right here, first of all, there's a normal force and also a weight force that you act on. And there's also another force, which is the centrifugal force, so FC. So there's a weight and force acting on you. However, you are actually feeling your apparent weight, which is magnitude of the contact force that supports you. So when the rider's at the bottom, the normal force is supporting the rider, so the apparent weight is equal to the normal force. So the apparent weight, this is apparent, so that's the apparent weight is equal to normal force. We know that the apparent weight is equal to normal force, which also means that the apparent weight is greater than your true weight, which is why people will feel heavier at the bottom of the circle as you go up. So you can also prove this by using equation. The net force is equal to the normal force minus the weight, and the net force is also equal to the centrifugal force, so the mv squared over r. And this is also equal to and is equal to the apparent weight. You can say that the apparent weight minus the weight is equal to mv squared over r. So your apparent weight is equal to mv squared over r plus your weight. So you can see that if you're going faster or any speed, then it's always going to be larger. The apparent weight's always going to be larger than the actual weight. So and you always feel the actual your apparent weight at the bottom. So it'll always be larger. So that's why you feel heavier when you're at the bottom. So now we'll be talking about the apparent weight circular motion when you're at the top. So when you're at the top, right here, you can see that the forces acting on you are the normal force and the weight. But when you're at the top, actually, the normal force, instead of like facing upwards, let's say this is you, it's also facing downwards. So your normal force, your weight, and the centrifugal force is all going downwards. So the normal force is actually pushing down, and the weight is also pushing down at the top, and the net force is downwards towards the center of the circle. So the net force is equal to the normal force plus the weight, which is equal to mv squared over r. And since the weight, apparent weight is also equal to normal force still, you can say that the weight apparent plus the weight is equal to mv squared over r. So the apparent weight is equal to mv squared over r minus the weight. So the apparent weight will be less than the weight depending on the velocity. So if the velocity is 0, then it'll be equal to the weight. But usually when it's velocity going faster, this will be very large, and subtracting it by the weight will make the apparent weight really small, causing you to feel weightless. So now we're doing some problems. So you have 2 minutes to do problem 1. Okay, so for this first question, it it says a 250-gram ball is being swung faster and faster in a horizontal circle. So the ball is like here and it's going around. When the speed reaches 15 meters per second, the tension is 5 newtons and the string breaks. So like the string right here breaks. What is the radius of the circle? So in this case, the centrifugal force is equal to the tension of the rope, which is 5 newtons. So you can write the tension is equal to mv squared divided by r. So trying to find r here, so it would be r equals mv squared divided by t. So it would be 2.5 times 15 squared divided by 500, and you would get 11.25. Oh, okay. It would be 0.25 meters, and in centimeters it would be 11.25. So this is the solution. Okay, so you guys can do question 2. Okay, so this question asks, um, in 5 kg object moves on a circular track of a radius of 18 centimeters with a constant speed of 6 meters per second. Find the magnitude and direction of the acceleration of the object. So to find the acceleration, it would be a equals v squared of r. This is centrifugal acceleration. So to find that, you know the speed is 6, so it would be 6 squared divided by 5, the radius, which is 0.18. So it would be 15 meters per second squared. And for B, it asks net force acting upon the object. What? Um, what is the net force acting upon the object causing deceleration? So it would just be the centrifugal force, which is mv squared over r. It would be 5 times 36 divided by 0.18. The base is 0.18 because you should the distance should always be in meters. So this would also equal to 250 meters. You understand? This is the solution. Oh, I forgot to answer. It says the direction of the acceleration, and direction is going to always be towards the center of the circle. Okay, so you can do question 3. Okay, so for this question, it says you are riding a roller coaster going around a vertical loop on the inside of the loop. If the loop has a radius of 50 meters, How fast must the car be moving in order for you to feel 3 times as heavy at the top of the loop? So to do this, we'd use the weight plus the normal force is equal to mv squared over r. So it'd be since you're trying to find 3 times as heavy at the top of the loop, it would just be w the weight plus 3 times the weight is equal to mv squared over r. So it's just 4 weight equals 4 mg. So it would be 4 mg equals mv squared over r. So, and it asks what the speed is, so it'd be 4 r equals v squared. So that would just be v equals 4 gr. And we know the gravitation due to acceleration is 10 meters per second squared. And the r is given as 50 meters. So the answer is 44.3 meters per second. Okay, so now you can question. This is the solution for number 3. So now you can do question 4. So for question 4, it says a Ferris wheel ride has a diameter of 10 meters and uh, is moving at 5 meters per second. So what is the centrifugal acceleration of the cart? So using the equation AC equals v squared over r, we can find that since we know the velocity, which is 5 meters per second, so it's 5 squared divided by the radius, which is 10. So 25 over 10 is equal to 2.5 meters per second squared. So this is the solution here. Okay, so you can do question 5. And I'll give you like 2 minutes to do this. Okay, so for this question, it says an insect sits at the edge of a slowly turning wheel. The wheel is accelerating gradually until the insect can no longer hold it on. The insect's path of travel will be number 1, the insect will move away from the wheel in a straight line perpendicular to the wheel edge. Number 2, the insect will move away from the wheel in a straight line tangent to the wheel. And number 3, the insect will move away from the wheel edge in a curvilinear path. Or 4, the path is not predictable by Newtonian physics. And 5 is none of these is true. So the correct answer is 2. Because as I said before, if there's no force acting on something going in a circle, then it's just going to move tangentially away from this thing, from this circular path. So it can be perpendicular to the wheel edge. It can't, or also be like that, and it's not going to move in a curved path like this. And 4 and 5 are wrong, so it's 2. So you can read the solution right here. Okay, so you do question 6. Okay, so for this question, it asks, for an object traveling in a circle at a constant velocity of 100 meters per second, which of the following is true? So if we look at the possible answers, the fourth one says the radius of a circle is 10 pi, and we wouldn't know that by just using velocity, so that one's wrong. The only gravitational force is acting on the object, that's also wrong because the centrifugal force is also acting on it, and no forces are acting on the object. That's also wrong. So it'd be okay. And that's also because the acceleration is always constant, and a circular motion that has a constant velocity. Yeah, you can read the answer here. Okay, so this is this is problem 7. Okay, so for our final question, it says a ball of mass 1 kg is on a string of length 2 meters. If the ball is being spun in vertical circles at a constant velocity, uh, um, and with a period of 2 seconds, what is the maximum tension in the string? Okay, so the tension, since it's going vertical, it would be the centrifugal force plus the gravitational force. And so it would be m times centrifugal acceleration plus m times g. So we already know how to find mg, we already know the answer to the mg. So now we're trying to find the centrifugal acceleration. So it would be AC is equal to v squared over r. So we know that v is equal to 2 pi r times the period. But this tells us the frequency, which is 1 over f. So that means that it would be 2 pi r over f. So it would be 2 pi r. Oh, sorry. It would be this is f and this is t. So it would be 2 pi r divided by 2. So it would be pi times r. So that's the velocity. So v would equal to pi r squared divided by r. That would be pi squared times r. So if we put that in, it would be so it would be, so we find that AC equals pi squared times r. It would be m times pi squared times 2 plus m times 10, which is g. So since we know the mass is 1, it would be 1 times pi squared times 2 plus 10 times 1. So the answer to that would be 29.7 newtons. So this is another way to do it right here. In the solution, they put the period as p. So they found the velocity is 2 pi over p. So they plugged that back into the equation and got 2 pi r over p squared divided by r, which is 4 pi squared times r over p squared. And then substituted it back into this equation. So it would be m times 4 pi squared r over p squared plus the gravitation or acceleration. And then they did 1 times 4 pi squared times 2 meters divided by 2 seconds squared plus 10 meters per second squared, and got 29.7 newtons. Okay, so that'll be it for today's class. Thanks for coming, and have a great weekend.